All right, so today we're going to deep dive into some pretty fundamental stuff. Uh, the second law of thermodynamics.
Yes.
And, as a sophomore mechanical engineering student, you're going to be knee deep in this stuff for the next few years.
This is the heart of things.
Yeah, so we're going to be looking at chapter 5 today and hopefully make it a little less intimidating. Because I know when I first saw all those equations,
It can look scary,
yeah, it's like, whoa.
but it's really not that bad.
No, once you get the concepts, it's pretty amazing how much this law actually governs.
It really does. The second law is everywhere.
Everywhere. It's like, it tells us why our coffee gets cold.
That's right.
It tells us why we can't build a perpetual motion machine.
Yeah.
All this stuff that, maybe we take for granted, but there's some really cool science behind it.
Exactly. Think of it this way. Like the first law told you how much energy there is, but the second law tells you what you can actually do with it.
Okay. So it's not just about conservation anymore. It's about
It's about the flow. It's about the direction.
the direction. Okay, so like how that energy actually behaves,
Yeah.
not just how much of it is there.
Exactly.
So, okay, that's a great way to put it. So then, like, why can't I unspill a glass of milk?
Right.
Or like, why does my coffee always get cold, even though, like, theoretically, the heat could flow back into it, right?
Exactly. And those are perfect everyday examples of the second law in action. The processes tend to happen in one direction, toward a state of equilibrium.
Okay.
So that coffee is going to cool down to match the room temperature. That spilled milk isn't going to magically leak back into the glass.
Right.
And that's because the energy naturally flows from higher concentrations to lower concentrations.
So it's not that it's impossible for that to happen in the reverse.
It's just not spontaneous.
It's not spontaneous.
Yeah.
It's not going to happen on its own.
Right. If you had some, crazy contraption to gather up all the spilled milk molecules and put them back in the glass, but that's not going to happen on its own.
Right.
That's work that needs to be done.
So even if I had some crazy, Rube Goldberg machine to get all those milk molecules back in there, the second law is basically saying, nope, not going to happen.
It's all about the direction of that energy flow, right?
Right.
And for you as a mechanical engineer, that's key because this has huge implications for anything you design: engines, power plants, refrigerators.
Okay, cool. So chapter 5 jumps right into 3 major uses of the second law.
Mm.
Determining the direction of processes,
Right.
understanding energy quality,
Yeah.
and setting theoretical limits.
All right.
So let's break those down one by one. Let's start with direction.
Sure.
So how does the second law help us figure out which way a process will go?
Well, let's go back to that heat engine example. Imagine you're designing a heat engine.
Okay.
The second law tells us that heat will naturally flow from the hot source to the cold sink.
Right.
That dictates the direction the engine can operate in. It can't just decide to run in reverse on a whim.
Okay, got it. So no perpetual motion machines, no matter how clever we get.
Exactly.
It's like the universe put up a big do not enter sign for certain processes.
Exactly. You just can't violate that.
Okay, that's a good way to put it. So we've got direction. Then there's this idea of energy quality. And that sounds kind of subjective, right?
Well, it's not really subjective. It's really about how useful that energy is.
Yeah.
Some forms of energy are more useful than others.
Okay, so like a roaring fire versus the warmth radiating from my lukewarm coffee.
Perfect analogy.
Okay.
That fire has high quality energy because it can be readily used to do work. You can use it to boil water, to generate electricity.
Right.
But that lukewarm coffee, not so much.
Right. Okay. And the second law helps us quantify this difference in quality, like put a number on it.
Absolutely. It gives us tools to analyze how energy degrades as it gets used. For example, in a power plant, high quality energy from burning fuel gets converted to electricity, but some of it's always lost as lower quality heat to the environment.
Right. Okay, so we're always going to have some losses. Which brings us to that third use, setting theoretical limits.
Right. And this is a big one for engineers.
Yeah?
Because no matter how perfect your design is, there's a limit to how much of that high quality energy you can actually convert into useful work.
So are you saying there's no such thing as a 100% efficient engine?
That's the harsh reality that the second law reveals.
Okay.
And this isn't just about friction or design flaws. It's a fundamental limit imposed by the universe itself.
So even in a perfect world, with zero friction, magical materials, we'd still hit that efficiency ceiling.
You got it.
That's kind of mind-blowing.
It really is. And it's not just a theoretical curiosity. For engineers, understanding these limits is crucial for designing realistic and efficient systems.
Okay, so let's get specific then. Chapter 5 dives into heat engines. What are they all about?
So imagine a device that takes heat from a high temperature source,
Okay.
converts some of it into work, and then dumps the rest into a low-temperature sink. That's your basic heat engine.
So like a car engine.
Exactly.
Got it.
It burns fuel, that's the source, makes the car move, that's the work, and gets hot in the process, that's the sink.
Right. Okay, that makes sense.
Power plants work on a similar principle, just on a much larger scale.
Got it.
And the key concept here is thermal efficiency. It tells you what percentage of that heat taken from the source actually gets converted into useful work.
And we already know, thanks to the second law, we can never hit 100%.
Right.
Like,
And that's where the Kelvin-Planck statement comes in. It basically says you can't get something for nothing.
okay.
There has to be some heat rejection to a lower temperature sink.
So no matter how cleverly I design my engine, there's always going to be some waste heat.
Exactly. And that's a key takeaway.
Okay. But the Kelvin-Planck statement isn't just about, crushing our dreams of perpetual motion.
No, it's much more than that.
It's actually a powerful tool for understanding and designing real-world systems.
Exactly.
How so? How does it help us in practical terms?
Well, think about it this way. As engineers, we're always trying to optimize for efficiency.
Right.
Knowing this fundamental limitation helps us focus on what's actually achievable.
Okay.
We can start asking more targeted questions, like how can we minimize those unavoidable losses? How can we design the engine to get the most work out of that input heat, even if it's not 100%?
So it's about having realistic goals.
Right.
Instead of chasing after this impossible 100% efficiency, we can focus on making the best possible engine within the limits of the second law.
Exactly. It's about working with the universe, not against it.
Okay, I like that.
And that's a key mindset for any engineer.
Okay, so heat